Hello friends, today we are discussing our seventh lecture that the topic is toolpath generation. Toolpath generation is a critical step in additive manufacturing that involves converting a 3D model into a set of movement instruction for the printer. These instructions determine the path followed by the printhead or nozzle to deposit the material layer by layer fashion. Myself, Dr. Debal Pramanik, Assistant Professor of SVIST, discuss about the toolpath generation. The term toolpath applied normally to conventional manufacturing. In additive manufacturing, the tool refers to the nozzle or deposition head or the high energy source that aids the material addition. Toolpath is used to fill the inside of the contour generated during slicing, and it provides the path to be followed by the additive manufacturing tool to fill material inside the contour. The pattern followed for toolpath influences the microstructure growth, residual stress pattern, surface topography, surface quality, distortions, and mechanical properties. There are several toolpath patterns in additive manufacturing. First of one is jet pattern. Jet pattern is the simplest strategy in which the additive manufacturing tool moves in a straight line along x or y axis for material addition. Later, we see the picture of jet pattern. The direction of scan vector is same for all the straight lines during the process, and starting point of all the vectors are in the same side of the part. This technique is most commonly used in additive manufacturing techniques, where the energy source is scanned to solidify the feed material, that is in VAT photopolymerization, directed energy deposition, and powder bed fusion. The major advantage associated with jet pattern is easy implementation and simple algorithm. The major limitation of jet pattern is the reduced contour accuracy due to discretion errors at the edges not parallel to the scan direction. Next pattern is our S pattern. S pattern is an extension of jet pattern in which the two parallel rasters are connected by a linear scan path additive manufacturing tool movement. In ladder, we see the S pattern structure. During S pattern, the scan vectors are continuous and the scan vector moves from one vector to the next without any delays or jumps. The major advantage of S patterns are easy implementation with simple algorithm and higher build rate due to material addition in both the scan direction. The major limitation of S pattern is the reduced contour accuracy due to discretization errors at the edges not parallel to the scan direction. Next one is your spiral in or out pattern. Spiral toolpath can be used from outside to inside or inside to outside. Spiral in or out pattern consists of sequence of patterns generated by creating contour parallel to or offset from the boundary as presented in figure, that is, we are discussing in later. The pattern used for scanning from outside contour to the center in spiral in pattern, and scan pattern from center to the outside contour is spiral out pattern. This strategy provides a solution to avoid excess heating and temperature accumulation at the edges. This aids to reduce the distortion or deformation in the additive manufactured component due to reduced thermal gradients. Another advantage is the similar number of tool passes. The major disadvantage are the complex algorithm and different to implement's nature. Spiral in result in larger distortion at the center of the build layer, while spiral out lead to distortion of the heat outwards resulting in reduced thermal distortion. Today, we are discussing 3 different toolpaths in additive manufacturing. Thank you.